Okay, so we're trying to represent um, the straight line as a parametric curve. Um, so we're sort of doing it from scratch, even though we know what a straight line is in an xy plane, a function x of y, a function of x. So we know how to do that. But it's really a bit of a dead end for us to try to pursue that, because the vertical lines are not parametric curves. Are parametric curves, but they cannot be represented as functions, as graphs of functions. So just as well we could start from scratch. The idea already is there. We interpreted things as in terms of motion. So xy plane is our sort of plane field. It's not independent variable anymore. Both of them are dependent. So the idea then is to express x in terms of t and y in terms of t. We interpret them as motion. The simplest kind of motion would be motion with uniform velocity. And we choose one relative to x and y separately entirely, so treat everything separately just as we have before, just the input variable is the same. That's the only relation between the two. So we're imagining that we're moving on the xy plane along a straight line, and we do it in such a way that the velocity is uniform. So as you can see, I circled there in orange what we're doing, and we are thinking about moving along the x-axis, along meaning parallel to the x-axis. We're not on the x-axis, but in a way it is as if that's exactly what's happening. So it's imagine that the motion is on the table, and then you have y-axis is going this way, x-axis is going this way. So to see the x motion with respect to the x-axis, you might do something like this, and you're looking at it so that this is my x-axis. And there is no, you can close one eye so that there you don't have any sense of perspective, and so you don't have any depth perception, and therefore the y direction is as if it's automatically ignored. So once again we have a plane, and I have, just for my own convenience, I have x-axis here, and say y-x is there, okay, to create a record. And then initially I could, so there's a motion there, and I'm here, I'm looking at it, okay, well, maybe not, so one eye, okay, so one eye, so there is no perspective, and then once again there is no depth perception, and the y direction is ignored. So all I'm seeing, this is my motion, hypothetically, but this is what I'm seeing is motion which is entirely left-right to me. Okay, so then and then I'm just investigating that, and then so what I'm saying is that my equation will be very simple. It will be if the horizontal relative to x velocity is m, then I just multiply it by t. So starting with x naught, initial location, is x, and then every unit of time I progress m units to the right. Okay, so where am I? I just x naught plus mt. Okay, and then naturally what I do is I do the opposite. I now not the opposite. Now I do the same with the y-axis. So I'm here somehow, and once again I'm looking at what's going on the x-axis. And my once again the depth perception relative to the x-axis is gone, and all I can see is this motion like this. So left, right, like this. So this person sees this, and the other person sees that, left and right, and then they sort of create a different. They collect different information and they produce different algebra. So predictably, the second person will produce the equation which is almost the same. Y is equal to y naught plus nt. And what do they have in common? Nothing. Just the t is the same. but you have initial location is y. What does it have to do with x? Nothing. And the velocity with respect to y is n, also is entirely arbitrary. So these are the four parameters of my motion. Initial location has two coordinates, and my velocities with respect to x and y have two different quantities. And then so these are two separate people produce two separate information. Then they pull the information together. That's what creates a parametric curve. In this particular case, the motion is especially simple because it is a straight line, and this is pretty much the answer to our question. And so let me just write it up. A straight line through the point x naught y naught in the direction given by n and m and n is given by a parametric curve x naught plus mt y equal y naught plus nt. Once again, I put that brace there to emphasize once again that they come together. Okay, so they are satisfied simultaneously. Okay, so it is a straight line, and then this is these 31st lines. That is the whole description of the line. It is very similar to let's compare it to calculus 1. So we would still speak of, so straight line, don't get a wrong idea here. This is still on the xy plane. So the situation seems to be very similar to calculus 1. Straight line on the xy plane. We just produce a different. We do it in a different way. Okay, in a more general way. So as you can see, so that's calculus 2. Calculus 1, it would be very similar. Straight line through a point x naught y naught once again, but instead of two numbers, we had one. Okay, so that, let's call it m. It was the slope. So we had a point. Remember, point on the xy plane and the slope m, and so my point slope form was y equal y naught plus mx minus x naught. Okay, so that was my equation in calculus 1 for a straight line. Okay, and so what is the relation? As you can see, the main thing to note is that instead of having three numbers to deal with, so x, y naught, x naught, these are the same. We have only one number instead of two. So slope m. This point is x naught, y naught, and slope m. So that is the calculus 1 setup. Now calculus 2 setup is this part is the same. It is point x naught, y naught, but instead of having one number for the slope, this is what we have. We have two numbers indicating progress, horizontal and vertical progress, like this. This is m, and this is n. Okay, so so what's the relation between the m capital and mn lowercase? M capital is m over n, right? M is equal to n over m. Okay, so that's how you slope rise over the run. So that's what we're looking at. What I described as velocities with respect to x with respect to n, they are in fact simply run and rise. So if you prefer that language, which is I guess okay, well, two different ones. M is the run and n is the rise. It is, of course, only happening on the xy plane. If you put it vertically, that xy plane, the rise makes sense to describe it this way. But really, with parametric curves, it's easier to think about the horizontal plane we're moving along it. Okay, so then that explains why having what extra number gives us. It gives us the possibility of having m equal to 0. So you cannot have you cannot go this way if your number m is equal to 0. You cannot. There is no slope. The slope would be infinite if you like. You certainly can go backwards, right? So if you have your calculus 1 description point slope form, then you can get an equation for the parametric representation of the straight line. All you have to do is just to suggest m and n. So choose. You have m capital given. What should you choose for m and n? Well, m is supposed to be equal to n over m. So you could choose any pair m and n as long as their ratio is m capital. So give me an example. I mean, you have, in a way, you have too many choices. So, well, give me one. It doesn't matter which one. Well, there is one, the simplest one. Which one is the simplest one? What's the simplest fraction? What kind of fractions are the simplest? Those aren't fractions, really. Right. So what kind of fraction that is not a fraction? Its denominator is 1. Okay, so that's the easiest way probably to choose m to be equal to 1. Right? So, and then m capital here. That's the easiest choice. So then, as you can see, this way works out always. From graph representation of a function to parametric representation. Backwards, as I just explained, it doesn't work always like this. So like this, only if m not equal to 0. So in other words, when the line is not vertical, then what's on the left is just as good. So we can go back and forth, but since there is a limitation going back to calculus 1, then we certainly know that we're gaining something to begin with, and not only that, we certainly getting more than just that, and we don't really want to go back seriously, because we are gaining just too much new possibilities for parametric curves than just the ability to have vertical lines, because there could be vertical tangents are the main problem in calculus when you encounter calculus 1, and the example that I had, I think, last time of the cubic root function, which is totally fine looking function like this, but it is not differentiable over here because the derivative is infinite. Okay, from the point of view of parametric curve, there is no trouble whatsoever, and so that's how you utilize parametric curves in order to expand your abilities to study nothing but curves. But let's be clear, really the motion idea is not as much as it could be a means to an end and a way to explain things, but motion itself is a worthwhile enough goal to go in this direction. So we really don't never going back from parametric curves to functions, considering that you have two functions anyway. Those are two functions. So we'll look at it. Each of these two functions is nothing but a copy of this. Okay, so linear function. So you had one linear function in calculus 1 for a straight line, and now for the same pretty much straight line you have two. So it's more stuff, but really if you look at it, it's just one extra number in order to you sort of save a little bit. On one hand, you have two numbers instead of one, but on the other hand, you don't have to divide those two numbers. So it's in a way it is simpler. So anyway, this is a straight line. Any choice of those four numbers, x naught, y naught, m, n, gives you a straight line. Once again, this picture is crucial in the middle. That if you are looking for example, a vertical line, you know that you're going to put m equal to 0 in order for it to work out. So as an example, m equal to 0, vertical, n equal to 0, horizontal, m is equal to n, diagonal, 45 degrees, so 45 degrees. So later on, when vectors are available, you can just combine m and n into one vector, and then just say that is the direction, literally, of which way you're going, and then you're treating the velocities as vectors, just as velocities and accelerations. Okay, so what else? So these are just lines, But if you are, remember that the main idea of calculus is that everything is replaced with straight lines, at least on the small scale. So if you have a curve and you zoom in on it, you're going to end up with a straight line. So that still applies. That idea still applies. And to parametric curve, that is, it is just in a slightly more complex way. But the idea is when it does work out and you have a straight line, then this will help you to know what's happening to your curve. For example, it will tell you sometimes when how your curve crosses, say, the x-axis or the y-axis. As an example, let me take an example. And after all, everything that we have learned about calculus 1 will be applicable twice. Okay, so x is equal to f of t, y equal to g of t is a parametric curve. Then we have two functions that came from calculus 1, so which means that we're going to be doing limits twice as much for each parametric curve, and then derivatives and same integrals. Every single thing from calculus is applicable. So if you want to understand what's happening to your motion or parametric curve, then you study x and y separately in order to understand look at the derivative, for example, look at where it is equal to 0, look at where it is positive, where it is negative. As an example, let me just give you an idea of what this is. How about this? F prime of s. S meaning I'm picking a particular s rather than throughout. So suppose f prime of s is equal to 0, but g prime of s is not equal to 0. Okay, so think about what we are. I'm sorry, not equal to 0. Okay, so what we're thinking about here is that the rate of change, you're progressing in the horizontal, you're not progressing in the horizontal direction, okay, but you are progressing in the vertical direction. Okay, so we saw that example yesterday. What does it look like? In the vicinity of a point, what does the parametric curve look like if you have these properties? It's probably more convenient if to put it this way: x prime is equal to 0, y prime is not equal to 0. So just once again renaming, focusing on the variables rather than functions. So x, variable, the dependent variable depends on t, y depends on t, and in particular location, so I don't know, x naught, y naught, you have this kind of behavior. The answer is that this is what your behavior, your curve looks like if you zoom in. So this is one location. This is just one location. If you zoom in, it's going to look like this. It's vertical. It might be going up or going down depending on what. So there's a vertical motion if you zoom in, and why vertical? Because there is no motion horizontal. There is no horizontal motion, which means that it is vertical. But which one? How do we determine we're going up or down?
Positive or negative?
What? What? N?
Yeah, like when you split it up into the...
Okay, yeah, but that's true. But that would work for a straight line. What is the analog of m and n for in general? It's the derivatives, right? So in fact, we're going up when y prime is positive. We're going down when y prime is negative. Okay. So all the ideas applies. You just have to look at them more carefully and well, actually it doesn't take a lot. You can make up a little bit of a table. Let me try it. So I will have x variable horizontal, y vertical, and then I will be looking at the derivatives of x and y separately. And once again, they exist separately. That's why every combination of x prime, y prime is possible. And I will look at x prime negative, x prime equal to 0, x prime positive. Okay, and then I have y prime negative, y prime 0, y prime positive. So I have 9 possibilities. The one we just looked at, we had 2. So I have, as you can see, x prime equal to 0. So I'm looking at the middle column. And this is what we're talking about. Okay, this is what we just talked about. X prime is equal to 0. There is no horizontal motion. Okay, but depending on the sign of the derivative of y, we're going either up or down. Okay. What about if I take the middle row? What do I get there? Middle row. So y prime is equal to 0. So what does it mean? Y prime is, well, once again, if you're not sure, think in terms of motion. And once again, x gives you your velocity with respect to x. That guy looking like this, and then the other one looking at the same motion like this. So, or you can think of yourself looking at maybe, I don't know, whatever that, a car that moves in some weird way, but there you can look at either at side window or straight window. So no, that doesn't work. No, I guess you need a side observer. So anyway, so if there is no progress, there is no progress. That's what the middle line is. Y prime is equal to 0. There is no vertical progress. Progress with respect to y coordinate, which means that the motion is horizontal, right? So only thing that remains is to see which way it goes, and once again, the x prime will determine which way you go, left or right. So x prime negative, so I will be moving left, and x positive, I'm moving right. So I'm talking about motion still on the xy plane. As you can see, it just happens to be horizontal or vertical along x-axis or y-axis, but it's still a three-dimensional motion. So the missing axis, well, actually, one thing worth mentioning is that this one is questionable location. When both x prime and y prime are equal to 0, you cannot say anything specific about this behavior based entirely on the derivative. So for an instant, you are not, or even for a moment, you're not moving pretty much in any direction. So there's nothing specific that you can you can say about it. So now what I have 4 cells left. So x decreasing, y decreasing. Which way are we going? Well, you don't have to think vertically, horizontally. It's probably a better idea to think I suppose the better idea to think north, south, east, west. So this x is about east, west, and y is about south, north, south. Okay, so as you can see, x prime is equal to 0, so we're moving entirely either north, or we're entirely moving south. But now if I'm looking at top left cell, then we're interested in which way we're going when x prime, y prime equal to 0, both of them. So we are moving, it still applies, we are moving west on one hand. On the other hand, we are moving south. Right, so well, this is the cell I'm investigating, and I'm just looking at x prime, and once again it indicates we're moving it to our left, west, and at the same time y prime is negative, so we're moving south, and altogether we're moving southwest. Like this. Okay, so in the same exact manner, I could add the missing arrows. So for example, here I'm moving, instead of moving, I'm moving east now. So it will be south, east. Okay. Over here, this one will be y prime is positive, which means we're moving this way, so it is north. So we're moving northwest. Okay, and this one, you can guess we are moving, whatever is left is we're moving northeast. So that's it. We're talking about the xy plane with the x's and y's replaced with the direction. So this is east, west, south, north. Okay, so the motion is on the xy plane, but directions, if you and I think it is preferable to think about motion in this manner, x and y on the horizontal plane, and that it will be easier slightly later on to add the third direction, the z direction. So that way we're going to have, it will be still a parametric curve, except it won't have 2 functions, we'll have 3 functions for x, y, and z, and then so the direction will be harder to figure out because as you can see, instead of 3 by 3 cells, you're going to have 3 by 3 by 3, 27 cells, and all kinds of different directions that you might go on your trip in space. Okay, so let me maybe, so south, this is no motion, and this is north. Okay, this one is west, no motion, east. Okay, so whatever in those rows and columns, those little arrows that are provided, you sort of combine them together in order to produce those green arrows. So for example, top left, I have, this is for y prime, and this is for x prime. Okay, if you combine these together, that's what you have. The actual motion is this. Okay, so that's called vector algebra. Okay, so as you can see, calculus 1 is superseded, but not discarded. So everything applies. So we're going to rely on calculus 1 fully. Okay, so straight lines. And we continue with doing some algebra, but not some calculus, which gives us algebra, and then we trace back to and provide some information about the parametric curve, which might not be plotted. Okay, so then for example, this table is very nice. You can also apply to how about the in a manner that's similar to calculus 1, you can apply to the circle, just to confirm what we have acquired through algebra purely, but we could take this table and apply to x cosine t, y sine t. Okay, to find out where it is going, how, so I differentiate. X prime is equal to negative cosine t, y prime is equal to sine t, cosine t. Okay, so then what you do, you study calculus 1 style both of these functions to find out where derivative is equal to 0, where it is positive, where it's negative. Okay, so we know everything there is to know about cosine, so that's why it's uncomplicated, but still it is worthwhile just to write up the conclusions. So once again, the problem is the method is find where meaning for what values of t, x prime is positive, negative, positive 0, y prime negative, positive 0. Okay, and then combine them together to according to this table to find out the direction of your curve. Okay, let me quickly do it. So you usually so you need to know where sine cosine are equal to 0, where they change the sign. Fortunately, that's no trouble. So I put here sine t, or negative sine t rather, over here, and I put cosine t here. I'll put my x-axis here, and I have to put the important points where the things change about these functions, and those are the multiples of pi, right? So it will be 0, pi, 2 pi, 3 pi, and so on. Okay, so, well, 4 pi. Hold on a second. 0 pi, hold on a second. Well, let's go with sine. So sine, we need to see where sine is equal to 0. Sine is equal to 0 at 0. Next time it is equal to 0 at pi. At 2 pi and 3 pi, it's all 0. Okay? Now, what about the sine? Between these values, sine does not change its sign. So what is it? On the 0 pi, what's the sign of sine? The sign of sine? Between 0 and pi? Going up and down. So I want to put something here. Do I put plus or minus? That's all. Well, when in doubt, that is sine. Well, that's not negative sine, unfortunately, but it's close enough. So this is my cosine. That is a sine. Okay, let me fix it. So I have negative sine. It is negative, like this. Okay, so negative sine t, and this is cosine t, cosine t. Okay, so sine changes its sign at every pi, and then in between it is negative. Between 0 and pi, it's negative, and then it alternates plus, minus, plus, minus. Okay? What about cosine? Where does it change its sign? Cosine, for what value of t cosine t is 0? What is this value? Pi over 2. Pi over 2, and then it crosses every pi. Starting from pi over 2, it will be crossing a 0 at every pi. So this is pi over 2, negative pi over 2, 3 pi over 2, 3 pi over 2, 5 pi over 2, and on and on. So that's where cosine is 0, 0, 0, 0, 0, 0. Okay, and then the signs alternate. Looking at the picture between negative pi and pi, negative pi over 2, pi over 2, it's positive, and then it alternates. So the behavior is predictable. And okay, so okay, so these are the plus, plus minus, and well, maybe let me maybe create more pluses. Plus, 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 minus, minus, plus, plus, minus, minus, plus, plus, minus, minus. Okay, so so the behavior changes every time we hit one of those points. So every pi over 2, there is a change of behavior, right? Because either sine or cosine change its sign. Okay, so then the behavior will be changing changing here. So within each of these bands, negative pi over 2, 0, 0 pi over 2, pi over 2 pi, 3 pi over 2, 2 pi, there won't be any change of behavior within these bands, but it will change every time as we cross the border. Okay, so let's pick the one once again, this one. Let me do it like this. Okay, so I'm looking at this band, the band of values of t. This is t over here. So t lies between 0 and pi over 2. Look at what we've got here. A negative sign is negative, okay? Cosine is positive. So what's the direction of the curve? You can refer to this table. So so once again, remember this is x prime and this is y prime. So it appears that x prime is negative and y prime is positive. So which way are we going? Right, so what is it, northwest. Over here, northwest. Northwest, and then as we cross pi over 2, what happens is nothing happens to negative sign, so x prime remains the same, so we're still moving west, but the y prime becomes negative. So I'm switching to this one, the next one. I'm at the next one. So so once again, no change in the behavior of x prime. It's still negative, which means that we're still moving west, but y prime changes from positive to negative, so instead of going north, we're going south. So it's a southwest. Okay? And then on and on. Next one is we are still moving south. Y prime is negative, so we're still moving south, but x prime becomes positive, so instead of we're moving now west, southwest. So now it's southwest, which is this. Okay, southwest, and then the next time period. So these, we took care of this. This is my fourth time period. Both of them are positive, so we are moving according to our table. When both are positive, we are moving northeast over here. Okay, so as you can see, that unlike in Calculus 1, I'm not trying to make up a curve from those arrows. That's what's very convenient in Calculus 1. I could just connect those arrows and I have my curve, but that's not the case. What we are talking about is consecutive changes of directions. So roughly speaking, what this constitutes is I'm moving northwest first, then I'm starting to move southwest, and I'm moving south east and northeast. That's how you should combine these two 4 arrows. Okay, so this is what you're going to get. So roughly, we cannot. So what is the message here? What do the derivatives tell us? What kind of motion is this? How would you describe it based on that picture?
They only tell the direction that it's moving in.
It is what?
Like the direction that it's moving in.
Right. So, but if you want to describe the whole motion during the between 0 and 2 pi, what has happened? Well, once again, let me. This is not here. Okay, so this is a continuous motion, and during first period of time we're moving in this direction, then the next period of time moving in this direction, then we start moving in this direction, and then in that direction. So the word that I would try to suggest is circular. Circular because we have changed the direction to the opposite of what we started with. Well, we didn't, but actually probably worth mentioning that the next one will be once again going northwest in the next one. Every 2 pi we'll start to repeat ourselves. So we cannot, that is a very rough sketch of what might happen. We certainly cannot guarantee that we end up at the same exact spot when we started. Based on this information, it's simply not enough. We only know the direction, so it could be a spiral, hypothetically. With this kind of description, you might go like winding on something or winding off something. All of that is possible, but it is kind of circular. So not circular literally, but kind of. So circle, square, that's a square. Circle, square, spiral, one or the other are still all possible. So that's what derivative supplies us with. They give us that information about rough directions and changes of directions, and we roughly can outline what to expect for the trip, but we do not know where we're going to end up. So that the derivative gives only partial information. And here with this is pretty good conclusion to describe the motion as a circular. If we know where we came from, so the actual answer is a circle. After all, it is sine cosine. We know this is a circle. So that should be a surprise that we ended up with a circular motion. So that's how we analyze curves based on their derivatives, parametric curves. Okay, so let me do something else here in this following the same idea. Pretty much, it is. So we had this is a circle once again. Remember this one? So it's a circle, and we have two functions, x and y, functions of t on the right. X and y are here as they depend on each other, and then the formula is sine and cosine, right? Now, what about ellipses? How would you compare a circle to an ellipse? Let me make this larger slightly. Well, actually, this one looks a little bit like an ellipse because the Excel resizes it, scales it so that it would fit the best. It actually creates, instead of a circle, we're still plotting a circle. It's just sine and cosine, but it is in fact disproportionately rescaled, creates an ellipse. Okay, so let me try again. So let me make it 2 over here. Well, in fact, make it 3. Okay, so that's a circle. I could make a circle of it as intended. Well, this is a circle. Well, more or less. As you can see, if I make those little squares on the xy plane, if I actually make them squares as meant to be, then our curve becomes a circle. So that's a circle. But it is also entirely my ability to do this, and then this is an ellipse. Ellipse is just a disproportionately stretched circle. If you do it proportionally the same in 2 directions, the same proportion, then it will be a bigger circle. But if you do it disproportionately, I actually did stretching only horizontal, it gives me an ellipse. Okay, but how do we do it algebraically? It's actually uncomplicated. It is simply, we have to add a coefficient here. So to stretch it horizontally, I will simply add here 2. So that's all there is. Let me. Well, as you can see, Excel rescales it again, having its own mind. So I'm trying to make it once again proportional. So one horizontal and one vertical should have the same scale as you would think. But, okay, so this is, it's a little bit excessive, but this is roughly, well, still no. This is roughly a square. Okay, as you can see, those squares on the xy plane are indeed squares now. And so the curve that we have plotted is indeed an ellipse. Okay, so as I said, once again, it is very easy to do algebraically. Ellipse is x a cosine t, y is b cosine t, sine t. If a and b are equal to each other, then you have your circle. Otherwise it is stretched. Okay, so and it creates a circle. Okay, where do in real life do we see ellipses?
Planetary motion.
Planetary motion, yes. Where is so suppose this is the Earth. Where's the sun?
It'd be, there are 2 centers in the ellipsis, so it'd be on
It's not the center. What's the word? Focus. So the sun would be here somewhere. Okay, so with all due respect to Copernicus, according to Kepler, it is an ellipse, not a circle. Okay, so the sun is located in one of the foci. But what I want to actually point you at is this is not the right way to represent the motion of the Earth around the sun. Anybody knows why? This is an ellipse, yes?
Is it because the motion of the Earth around the sun follows the z-axis as
No,
well?
no, actually it is interesting, but it is flat. It is a two-dimensional motion. It doesn't go any up, it doesn't make any complex motion. So there's a plane, and the Earth is moving within that plane. Now look at those dots. The dots are indicating the location, the consecutive locations of the sun, of the Earth around the sun. But in reality, the progress of the Earth is non-uniform. So in other words, we are moving like this. So we are moving here, we are moving slower. And then as we move away, we are moving faster. So in other words, the same path, but the parameterization is actually different from what is the most simple one that we derived from the parameterization of the circle. Okay, so once again Kepler. According to the Kepler, we are moving at a non-uniform speed. So we are moving slower when we're closer to the sun and faster when we're away from the sun. Right. Okay. All right. So see you tomorrow.